3. Hello, everyone. Welcome to Calculus Grade 12. And today we have class number 17 or even 18. I couldn't remember because we went so far in this course. And today we're going to practice once again what you discovered in the previous class. Yusuf,
Yeah.
can you remind me, please, what exactly we were talking about in terms of mathematics calculus?
Last class, what we talked about last class?
Yeah,
We talked about concavity and points of inflection.
yeah. So, and how concavity related to derivatives?
Concavity is related to derivatives and content and
Remember, we were
like
performing first and second derivative tests.
yeah. So
Yeah, go
yeah.
ahead.
Oh, sorry. The second derivative of a function can provide us information about the concavity of the function. Like the concavity of the function refers to whether the function is curved upwards, like concave up, or curved downwards, concave down at a particular interval.
Yeah, that's very good explanation. Because we can remember that if we would plot something like simple parabola, we have basically two intervals.
Yeah.
But the fun fact here that concavity is always up, isn't it?
Yeah.
Where, first of all, if we move from left to right here, value of our function f of x is decreasing. But the closer we get to 0, we see that this curve begins to bend back upwards and proceed to grow constantly, right? On the other hand, if we take a look on the upside down parabola, we're gonna see that concavity is pointing downwards all the time. Isn't that obvious?
Yeah.
And that's the parameter of our function that second derivative test can give us. So I suggest us move to some of the examples. First of all, outcomes. Of course, we're gonna practice problem solving from unit 4.4 in your reading material, and it's gonna be related to concavity and points of inflection. Particularly, we would start with the very beginning of this chapter. Alan, can you give me a hand right here?
Yeah.
So let's take a look at the point B.
Okay.
Here we can see that in the first part, we are asked for plotting the graph, which we just had recently, right?
Yep.
Here it is. This graph would be exactly the upper side of it. Am I right?
Yep.
And let's take a look. Determine the first derivative and
Okay.
calculate the slope of a tangent to a curve at some points. I'm not asking you to calculate those values. I'm asking you to explain how sign in front of the variable and value of the variable affects the information about first derivative.
Of the first derivative?
Yeah, so first derivative gives us some other specs of the function. What are those specs?
What do you mean by specs?
For example, like banded hula hoop,
Oh,
you know, it has a round shape,
yeah.
and we know that it has
Oh,
closed circle. It's specs of this object. And I'm just trying to explain you that derivatives of a
Yeah.
function, it's basically a way of describing the function.
I understand. So, the negative for the first derivative, in terms of the sign, it relates to the slope, the direction of the slope, or not the direction. How this, if the slope is increasing or decreasing. So if it's negative, it'll be decreasing. If it's positive, be increasing.
I would suggest you think about it in this way. Remember, first derivative, we can understand it as speed. What speed could be whether positive or negative, whether we're going downwards or upwards, or forward or back, right?
Mhm.
And first derivative is a rate of change, and rate of change is this velocity, right?
Yeah.
Am I not confusing you?
No, that makes sense.
Yeah,
So velocity determines direction where function goes. And here we can see that delta y is positive, right? That's what this gives us. And here we can see that delta y is going to be negative on the other hand, right?
yeah,
And in this case, first derivative is going to state on the direction rate of change, whether we're changing our state downwards or upwards. And second derivative would do what you just said, Alan. Second derivative would affect where are we moving, because here, even though the slope of a tangent line is negative, and it proceeds to be negative all the way up to x equals 0, right?
Mhm.
As if we substitute these values into first derivative that I wrote right here, can you see it?
Yeah.
We can see that it takes negative values, so slope of the tangent line is negative, looking downwards.
Mhm.
And once we're passing this point, what is this point called?
Which one?
X equals 0, y equals 0.
It's a starts with a C. A Give me a second. I know what it's called. Gotta find the name.
It's some special
Critical
points,
number.
some maybe important points.
Critical number.
Critical?
Yeah.
What critical number
Or
is
point of
x equals 0.
or point of inflection.
You're almost right. Point of inflection is when this arrow changes its direction. When this arrow from second derivative, right?
yeah,
Oh, local min.
Exactly. That's
Yeah.
what first derivative is about.
Mhm.
Points of inflection is when the curve looks like this. This is basically what is point of inflection.
Mhm. Yeah.
But this is another case. So great. So tell me, what would be the sign of a tangent line, of a slope of a tangent line to this curve to the left from 0 and to the right from 0?
The slope of the tangent.
What would be the slope of the tangent line, whether it's going to be positive or negative to the left from 0 and to the right from 0?
Which, like, you want the concavity or the value?
Whether it's positive or whether it's negative to the left-hand side from 0 and to the right-hand side from 0, to determine whether slope of a tangent line positive or negative. We don't need to calculate exact value, because all you do is substitute into this equation random value that is less than 0, right? In my
Yeah.
head, I
No.
could substitute here at -1000,
Negative.
wherever, but it's
Positive.
gonna be negative, and I don't care what coefficient it has. I just care about the sign, whether it's gonna be positive or negative. Make sense?
Yeah.
So tell me, what would be the sign of the first derivative?
Negative to the left and positive to the right.
Exactly. Are there tangents above or below the graph?
0. Nothing.
Are these tangent lines to the curve below or
Oh.
above the graph?
Oh. I misheard you then. It's below. It was
Mhm.
gave up.
Exactly. Now you see how it's all connected.
Mhm.
Here it was investigation at the beginning of the unit, and now you see how it works.
Mhm.
So Yusuf, can you describe the change in the slopes as x increases? Slope, remember, not in the value of a function, but in the slope of a function.
Like as it increases, like in this interval, the slopes of the tangent lines of the graph, like, oh, in other words, like, the function's rate of change is indicated by the slopes of its tangent lines. So, becomes steeper as x increases. So like when x increases within the concave up interval, the slope of the tangent lines to the graph of fx become less steep initially. Does that make sense? Or
Yeah, kinda. Becomes less steep.
yeah,
You know, you can say it relatively to the horizontal line because right now it's pretty steep, right?
yeah,
And it becomes less steeper. But then it begins to becoming steeper again, right?
yeah,
To the right hand side. But it's not exactly what changing was the slope. It's not becoming less steeper and then more steeper again. The slope is actually moving towards its positive value. Because if you substitute, for example, -4 into this equation for the first derivative, right? You're gonna
yeah,
get -8. That's -8 is a slope of a tangent line, right? We describe the slope as a coefficient constant number. It could be whether positive or negative, right?
yeah,
So if now we can substitute another value of x, and we can see that first derivative would be closer to positive. It would be -2, right? Not -8. We're not that steep into negative direction anymore, the way we were saying. And right after the local minima, it's called critical point. Do you remember critical point?
yeah.
Local extrema.
Locus tremor, yeah.
And then once we go into positive values of x, we can see that function is increasing. The first derivative is eventually getting greater and greater as x increases. So thus, the slope of a tangent line increasing. And it's increasing over a whole domain of a function. Because we are going from the most negative to the most positive value, and what we can observe in function x square, that over whole interval, over whole domain of this function, its rate of change is increasing.
Yeah,
Does it make sense?
yeah, that makes sense, yeah.
Can you say it in other words?
Like. I'm not sure how to say it, like better than how you said it, like.
No, you can use my words. I mean, just explain it how it's in your mind right now, because this really important stuff about physics and calculus in general. You know, who was the person that created the calculus? It was Isaac Newton, the person
Yeah,
who invented the gravity. And you know why he invented calculus? Because he once thought, wow, if the apple is falling on my head, it means the moon is also falling. And he was like, how is it working? How can I explain it? And in order to explain it, in his time, he didn't have mathematics of this level. He didn't have calculus. So he invented it. And calculus, what you see right here, is exactly what Newton studied, because you know how planets orbit around their sun in the solar system? On the orbit,
Yep.
elliptic orbit that has two focus distances, and it's mathematically proven concept, calculated specs of this elliptic orbits, and they're purely based on mass, on the force of gravity, and possibility to calculate it came only through analysis of simple functions. What is the speed of the falling apple? What is the weight of the falling apple? What is the gravity that is pulling this apple to the ground? If the Earth is creating this much gravity, it means that object that is this smaller, like moon, would create less gravity, right?
Mhm.
But it's us who can understand it in such way, because we already know about derivatives and Newton's law of physics. Newton didn't have Newton's law, first law and second law and third law of physics. Have you started them?
Yeah,
So yeah, Yusuf, you had enough time to think.
so like, if the function is concave up as x increases, like the slope starts small and then it increases, indicating that like the number represented by the function changes slowly. And like slowly at first and then faster over time, making it go like up. And like if the function is concave down as x increases, the slope starts steep, then decreases, indicating that the quantity represented by the function changes rapidly. Like it changes rapidly at first and then it slows down over time. That's like what I can think of right now and how to
That's really smart. That's
was
really smart, Yusuf. And you know why? You said that it begins to change its like speed less efficiently, right?
yeah,
And that's exactly what you can see if you elongate this parabola. Once you reach certain big values of x, you wouldn't see noticeable changes in rate of change. It would be almost, in terms of limits, vertical line.
yeah,
And we didn't talk about it. And Yusuf, you did a great job. I'm proud of you.
thank you.
Oh, don't you think so? It was really smart. I didn't even realize it when I was explaining it.
Yeah, it was really good.
So, did you copy this into your textbooks? Because this is really good visual support when you're trying to solve your home assignment, because everything is going to be based on this. It's just going to be in different shape, different formulas, but they're all going to be based on the sign of the second derivative, first derivative, whether it's concave up or concave down, or as a rate of change increasing or decreasing. So I
Yeah.
think we spent enough time on this one. Do you need a minute to copy it?
No.
No, I got it down.
Perfect. So here it is, example number 3. Interesting function to work with. Using the first and second derivative to analyze a root function. So you got a little hint here. And let's talk through this first step together, okay? So we have certain root function. And what we know about root functions? Root functions are not growing as well as quadratic functions, right? Because if I imagine function that has x that is constantly increasing, and this function looks like this, it means I have 1 over x to the third power, am I right?
Yeah.
The greater x, the less this number becomes. Oh, sorry, I did it's not right. It's not, it doesn't look like this, Yusuf. Why are you tricking me? This was x to the power -3, and we have a root function. It's gonna be a root of the third power of x, right?
Yeah.
And I was not right at first because this function would still grow as x increases. And it wouldn't exist for negative values. Am I right?
Mhm.
X cannot be a negative value. That's interesting thing to notice because function is undefined.
Yeah. True.
So, but let's find the derivative first. But it's really important to notice to yourself that x cannot be negative value. It's going to be useful for you when you're finding roots for example, for your first derivative test, when you need to solve for 0, right? So first derivative in this case would be pretty simple. It's just exponent power rule, right?
Yeah.
We bring the power as a coefficient in front, subtract 1, we have this. Now we flip it over, and by getting rid of this negative power, right?
Yeah.
So now we have 1 divided by 3 times x to the power 2 over 3, which is also equals to 1 over 3 in the root of a third power, like cubic. No, it's not cubic, it's just third power root of x squared. Am I right?
Yeah.
Yeah.
So know that this derivative does not exist at x equals 0.
Okay.
Can you explain why?
Because if you square 0 squared is still 0, and if you square root that by or cube root it, it's still 0. Multiply it by 0 or multiply it by 3, it's still 0. And then 1 over 0 is
Yeah,
or error on the calculator.
exactly. We cannot divide by 0. We can divide by 0 in terms of limits, but it's not the case, right?
Mhm.
So how would we call x equals 0?
Undefined. Or, yeah, undefined.
Critical number. Remember, you said it before.
Yeah.
This is the right moment. Remember, it is critical number x equals 0 of function of initial function, because we're doing all the thing to plot the initial function. And you get, even though the first derivative does not exist in this point, initial function is still defined and x equals 0. And it's going to be equal to 0, right? Alan, Yusuf?
Pardon me?
At x equals 0, our initial function that we're eventually going to sketch equals 0.
Yeah.
Okay. So what would be the next step for you guys?
You have your critical number, you could plot, you plotted that down. But why did you plot it down if x cannot equal 0? Why would it be a whole?
I plotted x equals 0 because we're plotting initial function, not the
Okay.
derivative.
Okay.
In this point, we can say that we don't know what is the rate of change exactly in this point. And this is because this point basically first, because x cannot be less than 0.
So your next step would be
Right now, for us, really important to determine how first derivative behaves as x approaches 0, because x equals 0 is a critical point, right? It's a first derivative test. And after we define the critical point, next step is define the
you'd find test points. So you would find points near 0, left or right, but in this case it'd be right. Plug it in and see where it would land on the y value.
another interesting thing, that first derivative would be always positive, even without us telling that it looking in the first initial function.
Yeah.
You see, so we don't have any problem. Math is working. This function is not defined to the negative value, right? And its derivative does not considers negative values.
Mhm.
So how would the function behave when first derivative is greater than 0? Oh, no, I'm so sorry. How first derivative would change as x greater than 0?
It would. Wait, let me think about it. It would increase. No, decrease. Would it decrease?
Yeah, I think so.
So remember, critical points usually stand for asymptotes. And those asymptotes could be horizontal and vertical, right?
Mhm.
Asymptote would be horizontal when derivative equals 0, and vertical when derivative is undefined. First derivative, it's first derivative test.
Mhm.
Am I right?
Yeah,
So at x equals 0, we're going to have a vertical asymptote. It means limit of a function as x equals 0 is infinity. And in this particular case, as x approaches 0, this infinity would be positive. Am I right? guys?
Yeah.
So we know that we cannot approach x equals 0 from this side, but we can approach it from here. So we're gonna substitute positive values of x, right?
Yeah.
Test points to see how the function behaves. And we know that from the right hand side, first derivative equals infinity. So it's vertical asymptote. And if we look into values of initial function, what it would be like. Any ideas?
What? Sorry.
About initial function, we define that at x equals 0, we have basically a vertical tangent.
Yeah.
And
um,
f-axis
goes to
increasing.
positive infinity.
Pardon?
And it goes to positive infinity.
Oh, actually, you know what? Hmm. What about it's a root of third power? It's not a square root. And I remember that only even powers are having problems in a root. So only even powered roots cannot be negative.
Yeah, so I just put on my calculator. You can cube root negative numbers.
Absolutely right. And you're gonna get negative number.
Yeah.
Because negative number multiplied by negative number 3 times is gonna be negative number. So basically we're gonna have a vertical tangent at x equals 0. In addition, f of x is increasing for all values of x, because now we see that we can substitute x less than 0 and greater than 0. You see, now we found the mistake.
Mhm.
Now we know that from both sides, from 0, our function, our first derivative is positive. It means that the function is growing up, right?
Yeah. And it's
So positive, the
to the
slope.
left, it would be decreasing to the left to negative infinity.
So it's not a local extrema. This point is not a local extrema because we're still increasing.
Is it a point of inflection? Because what I'm imagining right now is the graph would look like this.
That sounds about right.
So this would be a point of inflection.
Absolutely. And we're gonna see it once we perform the second derivative test. And it's really cool that you can already spot it. That's really great skill. If you can see it on early stage, it can simplify your whole solution because you already know where you're going, right? When we know where we're heading, it's much easier. So tell me about second derivative.
You just
This function is not so complicated to evaluate the second derivative too, right?
is it the power rule again?
Yeah, we're just again multiplying by the coefficient. But now we're gonna get a negative power in front.
Yeah.
Am I right?
Yeah. We're writing it down, sorry.
Take your time.
Okay, I got it.
And once we got second derivative,
And then you find the
and now
inner,
we can evaluate what sign it would have, right? We don't need to know exact value.
okay,
First of all, I would say that, again, first derivative, second derivative does not exist at x equals 0. For x less than 0, what about it?
it's negative.
So for me, it's looking not negative, not quite negative, because x to the power 5/3 is gonna be root of the third power of x to the fifth power, right?
Mhm.
And if we substitute x for negative value, we're gonna see that this denominator turns negative, right? Denominator negative 2/9 times x to the power 5/3. Right here, look. Can you see it? This is the second derivative. This is where we're
Yeah.
substituting our values now.
Yeah,
What you can say about it when x less than 0.
when x is less than 0, so. Let me just say, give me a second. So if you put, let's say you -2, random number, to the power of 5 divided by 3. Oh,
The easiest way is to substitute -1 or just 1, because it also satisfies interval x less than 0 or greater than 0. When that's how I evaluate it most cases.
-1 to the power of 5.
5, it's still
Oh,
gonna be -1.
wait. When I'm putting -1 in my calculator,
Yeah.
give me a second. It's not letting me square it by 1.66667.
Sorry.
I'm trying to, I put -1 in my calculator and I'm going to square it by,
Why would you square it?
or not square it, But it's-
You know, you need to put -1
yeah,
times -1 times -1 times -1 times -1 5 times.
and then
Oh, okay.
That's because x to the power
Oh, okay, so I have to do like that.
5/3 is equivalent to root of x to the 5th power. So if we substitute x
So
equals -1,
the power of
we're gonna
5,
have -1 to the power 5, which is equal to -1.
and then you cube root it,
And now
-1.
cube root of -1 is again -1. And this is sufficient for us because we would like to know the sign in this case, because we have product.
And
You
then 2
see,
divided by
this is the
-1.
beauty of functions, because if we had, for example, x plus 3x, it wouldn't be just a function, right? It would be some polynomial function. And here we're dealing with simple product, coefficient, multiplication, and where we're multiplying in first and second derivative test, we only care about the sign.
Okay,
Yes.
but how is the f, like right here, how is this a negative on top? Oh, wait a minute, because the entire function is to the negative. Okay, never mind.
It's negative in the numerator
Because
and denominator. It's not negative in the numerator because it's
Yeah, yeah.
-2.
yeah. So then that would be plus. Let me just write it down.
And again, x equals 0 is going to be critical point or point of inflection. Not critical, but this one is special point.
Yeah.
Critical points are in first derivative test, and in the second derivative test, we have point of inflection, and we can define concavity. Plus or minus of second derivative defines concavity, right? Whether curve looking upward or downwards. Make sense?
Mhm.
Yeah.
So, and here it's clear that we have plus special point, which is point of inflection, and minus.
Yeah, yeah.
And that's how you're gonna see it in most of the cases. You're just gonna have bunch of intervals in more complicated functions. You're gonna have more special points. You're gonna have bunch of intervals, and you just need to say plus or minus, plus or minus. It could be minus minus 2 times in a row, and it wouldn't be an inflection point, right?
Does this mean like the coefficient of the function? So it's positive, so it mean it'd be increasing.
Pardon?
What does this positive mean? Like the coefficient for like the sign of the coefficient or what?
So positive means like sign of the second derivative.
Okay, like the overall
As for
sign.
first derivative, sign determines the slope of a tangent line.
Yeah, yeah,
For
yeah.
second derivative, sign determines concavity. And concavity is nothing but basically tendency of the curve to grow or to slow down. Whether I'm speeding up my growth or I'm slowing down.
And
That's
then
what happens right here. Concave up, I'm speeding up, right?
what does the one for x equals 0 mean?
X equals 0 is an inflection point. An inflection
Okay.
point exists in those points where second derivative
Is
oh,
undefined.
usually inflection, we get a test whether critical points from first derivative test are inflection point or not.
Yeah.
Because if to the left and right hand side second derivative takes same values, then it is not an inflection point.
Yeah, I got it. I'm just gonna go use the bathroom quickly and I'll be back.
So let's take a 15 minutes break and get back
Okay.
to class. Actually, not 15. Can you are you still here, guys?
Yeah.
Because it's 6:53. Let's make like at 7 we continue and finish by 7:30.
Okay, sounds good.
Great. I'm back.
Hi.
Hi.
I'm back.
Oh, hello. So let's sum up. Yusuf, no, Alan.
Yeah.
Tell me about what first derivative told us about this graph.
The first derivative tells us the critical point. And if you plug in the terms from left to right, you could see if the critical point is a point of inflection. You could also see
Whether it's point of inflection, you see only from second derivative.
you just said it was from the first last time. No?
No, I said that you determine the critical point,
Yeah.
and in second derivative test, you see whether this critical point is also an inflection point or not.
Okay. So the first derivative is for the critical point. That's what you would find. And then the second derivative test,
How would you find the critical point?
you find the first derivative of the problem, and then you would substitute it for 0.
Then I would rather say you would look for,
Or you find the zeros, sorry. You find the zeros.
yeah, you find zeros or points where function is undefined.
Oh yeah, yeah.
Because that's exactly what we had in this example. Zeros are horizontal tangents line, right?
Yeah.
And undefined is vertical tangent line.
Yeah.
And secondly, we also can see what limit we have as we approach 0. And in
Mhm.
this particular example, we can see that the limit as we approach 0 is positive infinity from both directions. So limit same from left and right from critical point. It's positive infinity. So our function has vertical asymptote. Am I right? Oh, not asymptote, but vertical tangent line.
Tangent line, yeah.
Sorry, so you said for the first derivative test, the undefined equals the an undefined number would equal the horizontal asymptote.
No, opposite.
Vertical asymptote, and the zeros are the horizontal asymptote.
Sorry, not asymptote, but tangent lines.
Tangent line. Like, what do you mean by like the tangent line, as in like
Because remember,
this
first derivative, it's a tangent line at a point.
like this dotted line right here?
No, tangent line is the line that shares one point with the curve
Yeah, yeah,
and touches it like in one point.
yeah,
And that gives us rate of change of this
yeah.
function, instantaneous rate of change.
Okay.
So with first derivative tests, sorry, with second derivative test, we're looking for asymptotes if there would be some, for example, oh, actually, let me think, sorry. How would I explain this? So you remember the limit is basically an asymptote. Because when function is undefined, limit of this function approaching this point would be our asymptote. So value that we are trying to approach but would never approach. right?
Yeah,
It's a limit.
the limit, yeah.
And the value of a first derivative is a tangent line, basically, slope of a tangent line at a specific point. So when we substitute some values x into first derivative test, we're getting tangent lines always. This tangent line could be whether horizontal if if first derivative equals 0, right? So slope equals 0, horizontal line. Or it could be vertical if in this case we saw that in this case first derivative would be undefined in 0 and limit would be infinity. This is the vertical asymptote. Oh, but
Can you explain like something I could write in my notebook what the zeros mean?
you say that algorithm to sketch the graph is to perform first and second derivative test.
No, I already got that. Like I
First
just
derivative tests, you're looking for zeros
yeah,
or for undefined points.
I have that. So I just want to write
Second, after
zero.
that, just take this undefined points
Yeah.
and use them in second derivative tests to see whether it's inflection point or not.
Okay, so give me a second.
And zeros is just in these zeros, I mean, we solve function for 0. First derivative equals 0. We would like to see if there are solutions like that, right? In this particular case, there are no such solutions for first derivative. So thus, we don't have horizontal tangent line.
Sorry, so what's the way I could put that on my textbook? My book, sorry.
Didn't
Zero.
you say you already put it? The algorithm, first and second derivative?
I got the undefined point. If you plug into second derivative test, you could determine if it's an inflection point. But what about the zeros? The zeros are
When first derivative equals 0, you write f prime of x equals 0, then tangent horizontal line. It means that it's gonna be local extrema. Am I right?
Yeah,
okay. Yeah. Okay, I get it now.
And f prime of x does not exist. Or how would you say does not exist? You would learn it further, but you would say does f prime of x does not belong to rational numbers, right?
yeah,
Basically, that's what's happening when, for example, we have 1 over x equals 0. So this would be, let's say this is x1 and x1 equals 0 would not belong to rational numbers. And this most likely is going to be a vertical tangent line.
Undefined.
Yep, or undefined.
Oh, sorry, I was talking to Siri.
So can we move on?
Yeah,
Alan?
I'm just gonna have to write down what the second derivative test figures out though, and then I'll be good.
Yeah, take a minute.
The second derivative test determines whether the slope is positive or negative.
Second derivative test determines whether we concave up or concave down.
Okay. Is that all it determines?
And it also defines, depending on that, whether we concave up all everywhere, or we can concave up and down, or we concave down everywhere, we're gonna define whether critical point is a point of inflection or not.
And that's it.
Yes, but we're definitely not defining whether tangent line is positive or negative. Or do we? What we've seen before, that when we concave up,
yeah,
tangent line usually is below the curve. And when we concave down, tangent line is above the curve. So we also can see that. In this particular case, if we only know second derivative, for example, of this plotted function, we can see where it concaves, and we also can see if it concaves in such way that we have an inflection point. It means we change concave direction, right? So this is basically the only way to make such thing to happen. If you try to draw it in any other way, for this particular case, it wouldn't work. How else could you represent inflection point of a function that been concave up and then it's concave down?
Okay, I got it.
Of course, it could be in another shape. For example, like this. This is also concave up here and concave down after 0, right? Here is the only difference that y values are big, and we have two vertical asymptotes. Am I right? We have vertical asymptotes in this case. In previous case, we had horizontal one. Okay, can we move on?
yeah,
Example number 4. Determine any points of inflection on the graph. Oh, can you see my screen now?
yeah.
Yeah, sure. Determine any points of inflection on the graph of f of x 1 over x squared plus 3. So Yusuf, would you like to try it?
Try this.
Yep. Explain me the first step. And then let's move on to finding the points of inflection. So points of inflection are defined from second derivative test, right?
Yeah,
So what would be your first step?
to so the first thing is find the derivative of it.
Yeah, first step is find first derivative.
First
And
derivative.
second step is find the second derivative.
The second step, find the second derivative, and then substitute f prime of x. Right? No, or
Don't rush with that. Let's do step by step. Now you're set to find the first derivative. Tell me, how would you find the first derivative of this fracture?
just. I'm not sure how to explain it, but like,
No, why aren't you sure? It's pretty obvious. Remember, we used already today the power rule,
the power rule, yeah.
and not just the power rule, and also the thing that we didn't use in this case is chain rule,
Oh, the chain rule, yeah.
isn't it?
Yeah,
Isn't the
you can
quotient
use the
rule?
chain rule for this.
Pardon?
Is it the quotient rule or the chain rule? Which one?
Uh, remember in quotient rule, we have function divided by function, right?
Yeah.
And here we have constant divided by
Oh.
function.
Okay.
So this is not coefficient rule.
So it's just chain rule.
Yeah. Because we can simplify it by bringing x squared plus 3 to the denominator, but with negative power. And we
Okay.
can clearly see that this is internal function and external one. So what would be the first derivative? Can you explain it step by step what you bring out, multiply by?
Yeah.
Can we use the differentiation rules? Or,
Yes, differentiation rules, you must use them because
Yeah.
that's what the question is asking you to do.
yeah, so just take the derivative and then use the differentiation rules. And then just like solve it, and there's gonna be a zero somewhere, and let's just remove the zero.
But what is the first derivative?
Um,
How you find the first derivative from this? Because it's unit 3, it's before unit 4, right?
yeah,
That's why you do your homework.
So you want to find the the derivative of f multiplied by g of x. Yeah. So in this
G prime of x.
g prime of x. So in this right here, we want to put our what's our f of x and what's our g of x, or f of x would be
So first we find f prime of gx,
yeah,
f prime of g of x times g prime of x.
yeah. So
So
which so what is this one, our g of x, the x squared plus 3,
yeah, g of x is x squared plus 3.
or
F o g of x is x squared plus 3 to the power -1. So we bring this -1 in front and subtract 1 from the power. We get -2 and minus in front, right?
yeah.
Now we need to multiply it by what? Yusuf,
Multiply by
you just said it.
the differentiation rule or the derivative. Which one? Oh, the x,
G,
the g prime of x.
exactly.
So multiply it by the g prime of x,
And g prime of x would be
and g prime of x would be
your g of x is x squared plus 3, and here you simply apply sum rule.
oh, okay,
So you differentiate this
yeah,
and this is gonna be your g prime of x.
g prime of x, yeah.
And what would be a g prime of x?
You said the x squared plus 3.
Yeah, no, it's g of x.
Oh, the G
G,
prime.
s- G squared plus 3 differentiated would be G prime of X.
So, oh, okay, yeah.
So, Yusuf,
Yeah,
what is the G prime of X? What is the derivative of X squared plus 3? Differentiated,
the derivative of X squared plus 3.
yes. X squared plus 3 equals G of X. G prime of X equals X squared plus 3. Differentiated, right?
Yeah,
It's sum rule. You differentiate this piece and this piece, and you add them up. Derivative of the constant, what is it?
so the derivative of X squared plus 3 with respect to X would be 2X.
Yep.
And
Why we were looking for this?
we were looking for this because, oh, for the G prime of X.
And what do we do with it?
Then we, oh, substitute it there.
We multiply it by f prime of g of x. What we did in the step before.
Oh, yeah,
Bring this
yeah,
power in front as the coefficient.
yeah, and then,
Subtract 1. And it was our f prime of gx, right?
yeah.
And we have to multiply this by derivative of what is inside. So please tell me if f prime of gx equals minus x squared plus 3 to the power -2, am I right?
Yeah.
Times g prime of x.
So
Use.
yeah,
So what?
I'm not sure what the next step was.
Multiply.
Oh yeah,
You already have an
multiply,
answer on the desk.
yeah. So multiply f prime of x with. I'm confused now.
So product of these
Yeah,
is right here. This is the derivative, this line,
yeah. That's the derivative.
right?
Yeah,
Exactly what we did here. They simplified it by bringing it into the denominator. Am I right?
oh, okay, yeah,
Then they differentiated, applying power rule and the chain rule. Power rule to the outside function and chain rule because we have function inside.
oh, okay, yeah.
What is the chain rule, Yusuf?
Uh, oh, what is the chain rule?
Yes,
The chain rule was,
f of g of x and derivative of this. What is this?
It's F prime.
No. This is the function that we initially have when we differentiate it
Oh, you're at the prime of
and
that.
what we get. Alan, do you know answer?
For what?
What is the chain rule? What is the right hand side of this equation?
F prime of g of x times g prime of x.
Exactly. Yusuf, do you understand why?
No,
It's a
a
chain
little bit
rule
lost.
that we studied in derivative part,
Yeah,
derivative unit.
yeah, I remember the general, yeah.
So that's why derivative of f of g of x is f prime of g of x times g prime of x.
Oh, okay, yeah. That makes more sense, yeah.
Okay. So why we were doing this, guys?
Okay.
To find second derivative, right?
Yeah.
Yeah,
And we just found first. Yusuf,
yeah,
let's find second derivative.
okay. So for the second derivative,
This is the second derivative.
yeah.
Now let's think, why is it so?
Mm,
What do you need to differentiate?
But that one,
Exactly.
yeah.
And let's remember what rules are there for differentiation of a complex functions. Unit, this, I believe it was unit 3 point. No, this one was unit 2.3
Yeah,
or 2.2. You can check it out on our YouTube channel.
Is it the product rule?
Alan, you couldn't be better. Why were you so quiet if you know the right answer?
He called for Yusuf.
So Yusuf, you get a hint.
yeah, so the product rule you said?
Yeah.
But yeah. And especially not but product rule. Not only product rule, but also chain rule again.
Yeah. You use
Because in
product rule
product rule,
for
we
these.
have g of x
Yeah,
times f of x. But now we don't have just f of x. We have f of c of x, for example. Who cares? Any letter. Some composite function, right?
yeah,
So Yusuf, let's do it. Let's differentiate it. Come on. There, product rule, do you know it? I can help you with that, but you need to calculate it. Okay, I want you to calculate it.
okay, so differentiate,
I would write you the product rule. Product rule is as follows. Sorry, it's too crumpled up. I'll clear it and write it again. Product rule. Product rule. If we have two functions multiplied like this,
yeah,
f of x times g of x, we're gonna have f prime of x times g of x plus f of x times g prime of x. Do you recall it?
yeah,
So also we know the chain rule.
the chain rule, yeah.
Am I right?
Yeah,
So how do we combine these two rules together to find derivative of this?
Okay,
multiply
so
or
can I, never mind. Can I try to do it?
Yes, you can solve it with us.
Okay, so what I did was, okay, so I kind of just took, I didn't really look at the -2, so I figured out the -2x here. That's, or I'm gonna say that's f of x, and over here is g of x. So then I plugged it in, so I got -2 2x, and I took the g prime, which is just 2x. Why is it racing? And then plus -2, because that's the prime of f of x, or f, yeah, f of x, and then you get x squared plus. Are you erasing my work? I'm wondering where it's going.
You're writing. Oh,
There we go.
Alan, I believe you missed coefficient at the very beginning when you were differentiating.
Like that?
Mm, it doesn't look really.
And then I
But you also don't have -2 power. Why would you forget about it? Because you still have to carry it. No. You need to be like consistent in your approach, because if you try to solve bit from the end, bit from the beginning, it's becoming really hard. Can I show you my way of doing it?
yeah,
So what I do when I have a product, I'd break it up in two terms, right? -2x and x squared plus 3 to the power -2. If I would have just coefficient here, just some constant, not the variable, right?
Mhm.
Then it wouldn't be a product rule,
Yeah.
but now it is. So the next step for me would be just to follow general product rule, because this is, first of all, this is product rule. And secondly, this is chain rule for this one function inside, right? So
yeah,
first of all, my primary one is product rule. And I look here, f prime of x times gx. So from the left to right, this is going to be f of x, and this is going to be g of x. And not just g of x, but some like complex function, right? But we don't care at this moment. We're following this. And at this point, g of x remains unchanged. We just keep it as it is. Make sense?
Yep.
So follow me right here. Equal sign. It's going to be derivative of -2x. Derivative of -2x is -2. Am I right?
yeah,
Times this complex function, g prime of something, g prime of cx, for example, remain unchanged. So I just write x squared plus 3, -2. And I don't even waste my brain energy to determine what I'm going to write here. I'm just copying it directly. Then plus, because I know it's a product rule, I have plus here, right?
yeah,
f of x, now f of x is unchanged, -2x. So I'll write -2x times g prime of x. And now I remember, oh, of course,
Oh, okay.
g of x is a complex function. Now I have to apply chain rule. Okay. And I'm just simply applying chain rule as I did in the first step. with first derivative. But now the only difference is that my power is -2 instead of -1. Is it clear?
Yeah, it's clear.
So now I bring -2 in front as the coefficient, right? Is
Yeah.
it clear? -2 times what is inside to the power -2 minus 1, which brings us to -3, right?
Yeah.
And Yusuf,
And then
final, what is one missing part? What is that?
um I'm not sure what the final part, like,
G of X.
oh, the GFX.
No, final part is derivative
Derivative of G of
of
X.
what is inside.
Oh, so the
This is
square?
derivative, yeah. What is inside? X squared plus 3.
Yeah.
Same as happened in the last example.
Yeah, it was the same thing.
So how much I'm multiplying by?
3. Wait, no, 2.
2x.
Yeah, that sounds about right. And now let's simplify it. Do you need help to simplify it?
No, I can simplify it.
Can you
Yeah.
explain to us?
So just like just collect all the like terms. Oh wait, so first is calculate the products, and then we can like transform the expression into what's it called, like write it as like numerators and denominators, and
How can you write it as fraction?
um like when we were calculating the product, that's when we can like switch it.
No, I don't trust you, Yusuf. So first thing you said, right? We collect the terms, right?
Yeah,
What we can, group them up as much as we could.
yeah.
But can we do it when we have power here? Can we just bring this term inside the brackets?
Oh, we have to get rid of the powers first.
We cannot get rid of the powers. The only thing we can do with powers, if they're negative, is to flip them over,
Oh yeah, because negative, yeah.
or we can, in some cases, we can unwrap the squared function, combine it with terms, right? You
Yeah.
cannot just multiply what is inside the brackets by coefficient. You need to do the power function first. If Yusuf, do you know what's doing first? Plus, minus, or multiplication?
Multiplication.
And what if I have power?
Do the power first.
So if you have something multiplied by something into the power, for example, 2 times 2 squared,
Yeah,
you cannot do
yeah, you would have to do the power
you
first.
cannot do 4 squared. You
Yeah.
can't.
Yeah,
Is it right?
yeah,
So okay. Eventually, if you simplify it, first you bring the negative powers to the denominator.
Yeah,
Then you bring it to the same denominator to add up both nominators, right?
yeah,
Then you open the brackets, bring the common terms together again. Am I right? You're
yeah,
gonna have negative 2x squared plus 8x squared. And it's gonna give you 6x squared. Sounds right,
yeah, sounds right, yeah.
Alan?
At this, everything's right, but
Any questions?
yeah, right here. This step right here, you just added, like, right here, you just added, x squared plus 3 to the bottom, and then to the same thing you do to the bottom, you have to do to the top. This would,
Not added, but multiplied by.
this would have changed to 3.
Yeah,
Then you would have just an extra one up here.
yeah, you'll have x squared plus 3
Mhm.
here.
These ones could add together to become the same, and you would, okay.
That's it?
Yeah, just to reclarify.
Yeah, good. So yeah, they're not adding up, they're just
Multiply.
joining. Because what you see here is that you're dividing the product by this number. Because if you have 1 plus 2 divided by 2, it is equal to 1 divided by 2 plus 2 divided by 2. You're
Yeah.
gonna get 1.5.
Yeah, I got
If
it.
you 1 plus 2 divided by 2 is 3 divided by 2, 1.5.
Yeah, I understand that.
Clear. So why we were doing that? To find any point of inflection.
Yeah.
Am I right?
Yeah,
And once we got second derivative, what are we doing to find the inflection points?
We're gonna find the critical numbers for the zeros.
And we also can find those numbers from second derivative test by solving second derivative equals 0. How would you do it in this case? How this
Oh,
fraction can equal 0?
you could take your 6x squared, subtract 6, set that equal to 0. You just sub out a 6 or factor out a 6. And then you have x equals plus or minus 1.
Exactly.
Can you do the same for the bottom?
Another, huh?
Same for the bottom or just the top?
You also do the same thing to, you don't, first of all, you check whether denominator, that's what on the bottom.
Could be.
You
What?
gotta check if it can be equal 0 for undefined points.
It could be
In
0.
this case, this cannot be 0.
Oh, how come?
It's always positive.
Yeah.
Am I right?
Yes, it is always positive. Yeah.
So, and second thing, you have to check if you found roots for nominator, you gotta check if this value is okay with the denominator.
Okay.
In this case, it's okay with the denominator, but
Mhm.
you may get trapped.
Mhm.
It's okay?
Yep.
So we know 2 points. Right?
Yep.
And those 2 points are gonna be our critical points.
Mhm.
Sorry, not critical, but inflection points. We don't know whether they're critical or not. We don't know how first derivative behaves when we substitute those values in it. Right?
Okay, so
Those are just inflection points. So tell me, guys,
you need all these intervals? Oh, yeah, you do.
because you want to know how it behaves.
Yeah.
And you want to know whether it's really in fact inflection point or not. Alan, tell me.
Yep.
How we test it for whether these points are inflection or not.
So you put in your intervals, you want to find what's with marked down on the graph your 2 zeros. You want to find the points left, equal, and right to those points to find whether they're negative or positive or equal. If it is positive, it's concave up. If it's negative, it's concave down.
Yeah.
And if it's equal to 0, it's a inflection.
I couldn't say better. Alan, because it's exactly the right answer.
Thank you.
And here we came to an end of our class for problem solving for problems involving inflection points, concave up and concave down behavior of a function. And I hope you guys enjoyed the class. You had a really nice brain activity today. And I wish you all the best, and please do your home assignment and look for the new home assignment in your class folder.
Yeah.
Okay.
I look forward to see you again. Subscribe to YouTube channel and bye bye.
Thank you.